As Union Oil began to acquire offshore leases in deeper waters, the question arose, how will we produce them? One of the answers was with subsea completions, Christmas trees on the ocean floor. But Union didn't have a subsea completion anywhere in the world, so management decided before venturing into deep waters, deep water meaning below the effective working depth of divers, to install a deep water system in an existing field. That way, Union could develop the needed expertise and define the production characteristics of such wells. The Gulf of Mexico was selected for installation because of Union's vast offshore drilling and production experience there. During the summer of 1974, a state-of-the-art study was conducted of the systems then available. The study showed there were 5 manufacturers with functional systems. There were 2 types of subsea trees available, wet and dry. The wet tree is exposed to the marine environment. The dry is enclosed in a 1-atmosphere air environment chamber, which permits access by workers in shirt sleeves. All 5 manufacturers submitted proposals. The Lockheed Petroleum Services dry system, designed for use in up to 800 feet of water and 1,200 feet with slight modifications, was accepted because it had the best method of connecting flow lines to the well. The connection of horizontal flow lines to the well on the ocean floor in other systems is very difficult without the help of divers. The Lockheed method doesn't require divers for flow line connections. Other advantages of the dry system are that vendors can work on their own equipment as they would on land or a production platform, that it protects the electrical and hydraulic equipment from the sea, and that it provides more space to reduce equipment congestion. The main disadvantage is a dependency on a support system for access to the subsea wellhead cellar. Here's how the system works. A floating drilling rig drills a well in the usual manner, with the blowout preventer stack attached to a housing on the ocean floor. Tubing is run and hung in the underwater housing. The blowout preventers are then pulled. The wellhead cellar is then run and attaches to the same housing as the blowout preventers. The guidelines are removed from the guide base and the drilling rig leaves. The Lockheed vessel then comes to the location and anchors 150 to 200 feet from the wellhead cellar. A recall buoy is activated by a pinger and floats to the surface. A downhaul cable is brought up from the wellhead cellar by the buoy. The cable is attached to a downhaul winch in the skirt of the service capsule. The winch pulls the service capsule down to the wellhead cellar. The service capsule must be winched down because it is buoyant. When it reaches the wellhead cellar, it mates with the teacup portion of the cellar. An umbilical hose supplies air and electrical power and communications to the occupants inside the service capsule. The water is pumped out of the teacup and the skirt portion of the service capsule and is replaced with air at a pressure of 1 atmosphere. The pressure differential keeps the service capsule attached to the wellhead cellar. Entry is then made into the cellar. The buoy is released from the bullnose port, floats to the surface, pulling a line, which is then attached to the flow lines on a reel pipe barge. Using a linear puller, the flow lines are hauled into the bullnose port and secured. The reel pipe barge then lays the flow line to a production facility while the personnel install the Christmas tree and control system inside the wellhead cellar. Since Union needed through flow line or TFL capability, a horizontal wellhead cellar enclosing both the tree and the TFL tubing loops was ordered. Through flow line pump down tools are needed because ordinary wireline work can't be carried out on subsea wells. Instead, 2 flow lines and 2 tubing strings are run in parallel and are connected at the packer by an H-member. One tubing string, the production string, has a standing valve in the no-go nipple below the packer. The other string, the service string, has a plug in the no-go nipple. These tools can be pumped through a 5-foot radius bend, the TFL loop. The horizontal wellhead cellar could be ordered with the capability of operating at depths of 400, 800, or 1,200 feet. Since at the time the order was placed, it was not certain that this first system would be installed in 200 feet of water at Ship Shoal 269, an 800-foot cellar was ordered. It was felt that this would be sufficient for any location Union would want to install it. An extra 10-inch bullnose port was added above the standard 15-inch port for possible future installation of additional control lines, if they were needed to modify the control system. The Christmas tree was a 2-inch, 5,000-pound working pressure WKM triple with hydraulically operated fail-close valves. Both upper and lower valves were hydraulically operated, but the upper annulus valve was attached externally to the tree. A 16 3/4-inch, 5,000 psi working pressure Vetco H4 connector was ordered for the bottom connection of the system to match the system aboard the drilling rig Blue Water 2. A 16 3/4-inch Vetco SG1 wellhead system was also ordered, providing for 30-inch, 20-inch, 13 3/8-inch, and 9 5/8-inch casing and 2 strings of 2 3/8-inch tubing. This included a hydraulic set triple tubing hanger. The safety valves chosen were Hydrol's tubing retrievable well guard 2s, since a TFL retrievable valve could be installed inside the standard tubing retrievable valve if needed. The TFL valve would also be surface controlled. Vetco designed a special test block to isolate the control lines, permitting this well to become the first subsea well using surface control safety valves. A multiplex electro-hydraulic system was ordered from Kumi, and an electrical interface system compatible with Union's electronic supervisory system was ordered from Sizecor. 4,000 feet of double-armored subsea combination power and control cable was ordered from Vector Cable Company. An order was placed with Santa Fe Construction to spool 10,000 feet of 2-inch flow line on 2 reels of 5,000 feet. 5,000 feet of 1-inch hydraulic control line was also ordered. A TFL manifold that would serve as a lubricator for installation of TFL tools and a platform Christmas tree were designed and fabricated locally. A Halliburton T10 pump was ordered from Otis to provide a TFL pump. After all these items were ordered, a dry land test site was built. Before the system was installed offshore, it was fully test assembled onshore. A test stand was built at the dry land test site to simulate the guide base that is used on the ocean floor while drilling the well. The stand was built 5 feet above ground level, since the guide base is normally 5 feet above the mud line. A 16 3/4-inch Vetco H4 connector was the top connection. After the test stand was completed, the wellhead cellar was installed on top of the stand with cranes. The wellhead cellar at this point was a shell. It was fitted with all equipment and completely assembled. The bullnose was installed and the flow lines connected, and testing of the system began. The facilities which would go on the surface platform were installed in a building nearby. This included the TFL pump-down equipment and the necessary control systems. Between this building and the test stand, 2 3/8-inch flow lines were laid in a 1,200-foot loop to simulate the operational flow lines. An electrical cable and hydraulic line were also run between the simulated platform area and the wellhead cellar on top of the test stand. Since the test stand was not over an actual well, tubing strings could not be run in the ground. A 5-foot radius loop was installed under the test stand, which allowed tubing strings to be laid on the ground. The 2 tubing strings contained the downhole safety valves, the tubing position nipples, and the H-member with the standing valve and the plug in the bottom. The first test phase called for operation of all components as they would perform in subsea use. The second phase dealt with TFL testing, and once both were completed, a training session for offshore operations personnel was undertaken. After the training program was completed, the wellhead cellar was disassembled and prepared for shipment offshore. Then, since the wellhead cellar would be exactly as the personnel would find it on the floor of the ocean, reassembly was performed simulating underwater conditions as closely as possible. This included a flow line pull-in. All reassembly filming was also done at this time so as not to interfere with actual operational use. The system was given one final retest and prepared for shipment offshore. The well being prepared for Union's first test of the subsea system wasn't spudded in until the wellhead cellar was ready for installation, though it could just as well have been drilled and left until the wellhead cellar was to be installed. With this system, a well may be temporarily abandoned with an underwater housing attached, then be completed at a later date. The Blue Water 2, a semi-submersible under contract with Union, was moved to Ship Shoal Block 269 to drill the number 5 well in 200 feet of water. The site was selected for the subsea completion because a production platform was nearby, a platform with wells of known production characteristics. This well differed from the ordinary only in the use of a special guide base, with both 7-foot and 10-foot radius guide posts. A 7-foot guide frame was on the blowout preventers, a 10-foot guide frame was on the wellhead cellar. During drilling, the guide lines were connected to the 7-foot guide posts. 30-inch pipe was jetted in with the guide base. Then the 20-inch casing was cemented with the 16 3/4 Vetco H4 housing. The blowout preventers were then attached to the H4 mandrel. 13 3/8 and 9 5/8 inch casing were run and cemented, as is normally done. The 9 5/8 inch casing is the production string. The first step in the completion of the well was to gravel pack the production zone inside the casing. This production zone had no history of producing sand in the earlier platform completions, but it was decided to gravel pack as an extra precaution. After the well was gravel packed, it was drill stem tested following an acid job to remove plugging agents in the gravel pack. The tubing was run after it was determined that the well would produce sand-free. 2 strings of 2 3/8 inch 4.6 pound N80 CS hydro tubing were run simultaneously with a dual hydraulic packer with an H-member above. Below the packer were Q-nipples with a plug in the service string Q-nipple. The production Q-nipple was empty, and a ball trip sub was located below it to set the packer. 30 feet above the packer, 2 Otis Select 10 Position 1 nipples were located. A Position 2 nipple was located at 2,500 feet. The Hydral WellGuard 2 safety valves were installed in each string about 150 feet below the mud line. The Vetco tubing hanger was attached to the tubing strings, and the control lines for the ball valves were attached to the bottom of the hanger. Then the tubing hanger running tool was installed, and the hanger was run on a special completion riser built by Vetco. The completion riser had 3 2 1/16 inch bores and 9 1/4 inch bores housed inside an 8 5/8 OD. 2 of the 2 1/16 bores connected to the production and service tubing strings. The other large bore was the vertical annulus access. 4 of the 1/4 inch lines were used for operation of the downhole subsurface ball valves. The other 5 were used to operate the hydraulic running tool that set the tubing hanger. After the tubing hanger was landed, a terminal head was installed on top of the completion riser. A ball was then dropped and the hydraulic packer was set. A gamma ray color log was then run to determine the exact depth of the packer no-go and of the Q-nipples with relation to the production zones. This exact depth correlation is needed for future TFL perforating. Then a standing valve was installed in the production string Q-nipple. Diesel was displaced down the production string through the H-member and up the service string. The well was then flow tested. After the flow test was completed, the well was killed with salt water. The ball valves were closed. Plugs were then set in the tubing hanger by wire line. The tubing hanger running tool was released and retrieved on the completion riser. and a special tubing hanger protector was run on the completion riser to isolate the tubing hanger from any pressure above. After the tubing hanger protector was installed, the blowout preventers were disconnected from the H4 mandrel on top of the 16 3/4-inch housing and pulled to the surface. The guidelines were then removed from the 7-foot radius guide posts and reestablished on the 10-foot radius guide posts. This was done with a guideline replacement tool designed by Vetco specifically for this project. While this was being done, the wellhead cellar was brought to the drilling location by the derrick barge Tonkawa. The cellar had to be keel-hauled because it was too big to go through the spider beams. As this model demonstrates, the Tonkawa lowered the wellhead cellar into the water. The Blue Water 2 pulled the wellhead cellar beneath the rig as the Tonkawa let off. Then the rig pulled the wellhead cellar up to the spider deck of the drilling rig. Once the wellhead cellar was firmly attached to the rotary beams, the Lockheed wellhead cellar running tool was attached to the cellar. The wellhead cellar was run on drill pipe with a hydraulic hose bundle attached to the drill pipe while it was being run. The cellar was then attached to the H4 mandrel on the 16 3/4 housing as the blowout preventers had previously been attached. The connector on the bottom of the wellhead cellar was welded to a spool, on top of which was a blind flange which prevented seawater from entering the cellar. After the cellar was attached to the housing, the connection was tested to a pressure of 5,000 pounds per square inch. The tubing hanger test protector prevented this pressure from reaching the tubing hanger, and the blind flange prevented it from entering the wellhead cellar. After this test was completed, the running tool was released and retrieved. The guidelines were then removed remotely from the 10-foot radius post tops, and the rig was released to go to its next location. After the drilling rig departed, the Lockheed boat Coastal Cruiser arrived at the location, anchoring in a 4-point moor about 200 feet from the wellhead cellar. An acoustical device activated a pinger which fired an explosive bolt, releasing the recall buoy attached to the wellhead cellar. The buoy floated to the surface, unreeling a nylon line attached to a cable spooled in the teacup area. This cable is pulled to the surface and hauled completely out of the spool and into a 3-part bridle centered in the teacup. On the stern of the boat, the cable is attached to a winch located in the wet skirt area of the service capsule. The boat then launches the service capsule into the water, and the capsule pulls itself down the line to the wellhead cellar. It must power itself down because it has 2,000 pounds of positive buoyancy. If the cable breaks, the service capsule will pop back to the surface. Once the capsule reaches the wellhead cellar, a rubber gasket seals the mating surface at which the capsule and cellar join. The water is then pumped from the chamber formed by the teacup and the wet skirt. As the water is being pumped, the pressure in the chamber drops from hydrostatic to atmospheric. The differential hydraulic pressure over this area keeps the service capsule firmly attached to the wellhead cellar. After the water is pumped out, the personnel in the service capsule can enter the teacup area of the wellhead cellar. The pressure inside the wellhead cellar itself is immediately checked, as are indications of any hydrocarbons. If hydrocarbons are detected, or if the cellar has been inerted with nitrogen, the wellhead cellar is displaced with fresh air. Only after the cellar has good quality air is the hatch to the wellhead cellar opened and entry made into it. Only 3 of the 4 crewmen enter the cellar. The 4th man remains in the service capsule, monitoring the life support readings and maintaining constant communications with the control room on the coastal cruiser. After entry into the cellar is made, the crew begins to install the flow line pull-in equipment. The bullnose port has a special wafer with lockdown dogs attached to the flange on the inside of the wellhead cellar. Attached to this wafer is a large ball valve, which has a blind flange attached to it. After checking to make sure that ambient sea pressure is not leaked into the bullnose port, the blind flange is removed from the ball valve. A buoy canister containing an inflatable buoy, a hydro line stripper, a Bowen hydraulic line lubricator pack-off, and a linear puller are installed. A line is attached to the inflatable buoy, the ball valve is opened, and nitrogen is used to blow off an internal plug in the bullnose. The inflatable buoy is then pushed out of the bullnose and inflated with nitrogen through a small hose attached to the inside of the buoy canister. The hose disconnects automatically when the buoy begins to rise to the surface, and a check valve keeps the nitrogen from escaping. As the buoy floats to the surface, the line is fed through the Bowen pack-off and the hydro line stripper. At the surface, the buoy is brought to a lay barge and attached to the bullnose, to which the flow lines, control lines, and electrical cable are in turn attached. After it's securely fastened, the crew inside the wellhead cellar begins to haul in the line with a linear puller, while the lay barge reels out the pipe to the wellhead cellar. On this installation, 550 feet of pipe was pulled from the lay barge to the bullnose port in only 2 hours and 11 minutes. After the bullnose is secured and locked in the bullnose port, the lay barge lays the line to the production facility. The crew then removes all the pulling equipment and installs hull valves on the bullnose itself. A lubricator is then attached to the hull valve, and plugs are removed from inside the bullnose. These plugs would prevent water from entering the wellhead cellar if a leak in the flow line developed, after the pull-in equipment is removed and before the hull valves are installed. After these plugs are removed, the crew turns its attention to the tree installation. The blind flange on the bottom of the wellhead cellar is removed, as is the special tubing hanger protector, and a special test plug is installed over the tubing hanger to take the check valves out of service in the subsurface safety valve lines. The control lines and the subsurface safety valve lines are then connected. The tubing seals are installed in the two tubing strings and the vertical annulus. The tree is then bolted down and a wireline lubricator is attached to the tree to pull the plugs that were installed when the tubing hanger was run down the drilling rig. This is exactly the same procedure which would be followed on any other well. That is, the back pressure valve is installed in the tubing hanger, the blowout preventers are removed, the tree is installed, and the back pressure valve is then pulled. The TFL loops are then installed and connected to the hull valves. The control system is connected and the system is tested. All of this is done in a 1-atmosphere shirt-sleeve environment, though the well is many feet below the surface of the sea. On the last dive, the crew installs a new recall buoy and downhaul cable package. And after the wellhead cellar hatch is securely sealed behind them, its air is displaced with nitrogen to create an inert, explosion-proof, non-corrosive environment in the cellar. When the service capsule is back on the surface, the old downhaul cable is retrieved and the boat is ready to leave. While the coastal cruiser was working night and day, the reel pipe barge laid the flow lines and the control lines, including the electrical cable, to the production platform. The lines were connected in the conventional manner, using risers. A 5-foot radius loop was on the top and bottom of the riser. The TFL manifold had been installed along with the TFL pump and control system before the well was spudded. On the last dive of the service capsule, the control system was given its final check. Although a very simple hydraulic system could have been used to control this one subsea completion, the decision was made to install a multiplex electro-hydraulic system in order to provide experience with such systems. This is the type of system which would have to be used in fields with numerous subsea completions. A hydraulic override system could also control the well from this panel if the electronics failed. The well can be operated remotely from the district office, the Eugene Island 276 field, or from the platform by use of this annunciation panel. The annunciation panel outlines in lights, switches, and gauges the Christmas tree in the wellhead cellar. Each remotely controlled valve is depicted on the panel. The two subsurface safety ball valves are indicated here, one for the production side, one for the service side. These 4 valves depict the master valves, both production side and service side. This is the production wing valve. This is the service wing valve. Between the upper master valve and the wing valve, pressure can be read from the flowing tubing string, either the production side or the service side. This is the only valve that is fail-safe open. If the well shuts in, the crossover valve between the 2 flow lines will open. These 2 valves give access from either flow string, either the production or the service flow string, to the annulus. These 2 valves are the annulus master valves. This allows vertical access into the annulus. The annulus pressure can be read by opening the lower annulus master valve and the upper annulus master valve, which allows annulus pressure to be read at this point. The wellhead cellar pressure can be read in pounds per square inch. There will be approximately 1.5 atmosphere pressure left inside the wellhead cellar, or about 22 to 23 psi. The operating hydraulic pressure on this gauge tells how the hydraulic system is operating. The reference pressure is downstream of a regulator which maintains constant pressure to balance the hydraulic sequencing valves. These controls operate the valves sequentially. This is a master shut-in switch which shuts in everything, including the master solenoid valves. This switch shuts in the well without closing the master solenoids. This normally opens the well. This switch opens it from the production mode to the TFL mode. This returns from TFL mode to normal production. These switches open and close the valves in a normal sequence, as the pumper would if he had access to the hand wheels on the valves themselves. This button brings the annunciation panel into service. This button puts it back on the scan from the computer so the well can be operated either from Houma or from Eugene Island 276. After the systems were thoroughly checked out, the well was put on production on a beautiful Sunday morning in May 1976, 2 years after the initial study was undertaken. Why did Union Oil embark on this project? To be sure that Union will be ready to produce oil and gas profitably when it is found in deep waters. Years from now, when deep water production is routine, the lessons learned at the dryland test site and Ship Shoal Block 269 will have shown the way.